Good afternoon, everyone. We're the Caltech Air and Outer Space team, and today we're presenting CoverGuard. I'm Priyanka, and I'm joined by my co-founders, Parnika and Marcus. And we're a team of Caltech students with experience building and launching CubeSat payloads for high-altitude balloons. Today we're presenting CoverGuard. Cover crops are used across a wide variety of agricultural management systems and are the cornerstone of regenerative agriculture. Cover crops support long-term soil resilience and can increase cash crop yields by up to 40%. However, 1 in 3 cover crop plantings fail silently. This is because fields may look green and healthy, while the cover crop is too sparse or stressed to actually protect the soil in the long term, which can reduce cash crop yields by up to 15%. This introduces a critical monitoring gap when the cover crop has failed beyond the intervention window for farmers to act. CoverGuard innovatively addresses this challenge at a low cost. The CoverGuard pipeline begins on the ground. As you can see, we first start with the NASA HLS dataset and combine it with the NASA OPER dataset in order to evaluate vegetation indices, compute and segment imagery, and compute a field health score for each agricultural parcel. Low-scoring parcels are at risk of cover crop failure and are added to a target watch list, which is then uplinked to the satellite. On board, the multispectral imager adaptively images only over flagged parcels at twice the resolution of the HLS. Then these measurements are converted into 8 agronomic indices that each isolate a cover crop stress signal, such as NDVI, MSAVI, and NDMI, all at reduced computation.
The agronomic indices from our multispectral imager are first sent to our onboard light GBM classifier. Our classifier establishes and classifies 6 key cover crop failure modes, namely, establishes 6 key cover crop failure modes, namely moisture stress, excess wetness, nutrient deficiency, pest disease effects, and poor establishment, as well as unknown if confidence is too low. We are then able to do this with a classification accuracy of 96% in under 1 millisecond inference time on a low-power Raspberry Pi, as opposed to a costly NVIDIA GPU. Afterwards, we are able to compress this information into a key relevant 50-bit fault packet. This fault packet contains key parameters like parcel health score, likely cause of failure, confidence, location, and timestamp. And we're able to adaptively transmit these via a downlink algorithm, which computes an operational utility score as a function of fault relevance and fault recency. Overall, this allows us to deliver actionable insights in under 95 minutes. We also have a unique value proposition focused upon the fact that cover crop allows us to give the maximum operational benefit for cover crop applications. By imaging only the relevant parcels, we're allowed to reduce sensing by 80%, which increases mission lifetime 4-fold. By operating on a 3U CubeSat without a GPU, we also are able to reduce computation intensively and operate on an adaptive signature, which allows us to do actionable cover crop diagnoses within the intervention window. Afterwards, we adaptively downlink our packets. This allows us to reduce downlink volume transmission by approximately 90% and reduce the cost per alert by 50 times.
So while existing tools on the market each solve a part of the problem, none of them combine the low cost, broad coverage, and named multi-class failure diagnosis as CoverGuard does. With its compact alert size and rapid response time, CoverGuard gives agriculturists a faster, lower cost way of identifying which fields need their urgent attention. So, since farmers have slim and variable margins, instead of selling directly to them, CoverGuard sells a per-acre subscription service to agricultural businesses and conservation districts, thereby reducing financial volatility. With its compact alert size, it's a standardized format, so we're able to sell directly and integrate directly with existing farmer management protocols instead of forcing farmers to adopt new infrastructure. Furthermore, this architecture is easily transferable to other applications, such as wetland monitoring or forestry infrastructure. So we've already built and published our software stack. So our next step would be to create a high altitude balloon payload to flight proof our integrated hardware and software for further seed funding. Thank you.
Judges.
Great job. I love the focus and the use of the data for a specific purpose. But have you thought about these broader applications that you brought up on the other side? Because cover cropping, especially in the U.S., is not prevalent yet.
Absolutely. We decided to focus on cover crop here as we believe, it's great for regenerative agriculture. It's showing it's up and coming, especially. However, as I mentioned, because we're using this classification model, we can easily with new data kind of retrain and reposition ourselves to expand to other applications, such as that forestry inspection, as I mentioned, or even normal cash crop monitoring.
To add on to your question, one of the reasons cover crop farming is very sustainable but still not as prevalent in the United States is that it is harder to implement, and we're hoping that something like CoverGuard can encourage more farmers to use sustainable farming methods as well.
Anyone else?
Okay, there we go. So I think the balloon idea is really cool. I was actually working on a project with using balloons, so I was wondering if you could tell me a little bit more about the logistics, because I know you probably want to find the payloads again, and then are you going to have the farmers there release them, or would you need somebody from like a USDA or US Forest Service to go out on the land to release the balloons?
So in the past, our club has done 2 high-altitude balloon launches from the Mojave Desert. So launch logistics-wise, that's probably where we would launch from. We would definitely have farmers involved with the process. So far, we've been in communication with farmers up in Washington State. So we would probably bring them on to see what kind of insights are able to deliver and how accurate it is. But so far, our model has been trained on satellite imagery. So bringing in that in-person component with the high-altitude balloon is our next big step.
Very cool, and then I assume that's going to give you higher resolution compared to the satellite data, is that right?
Yes, we have twice the resolution of HLS. HLS is 30 meters per pixel, and we're suggesting about 15 meters per pixel.
Very cool.
Can you hear me?
Yes, ma'am.
Good job, guys. You shared a little bit about the score that's delivered from the downlink. Could you just unpack that a little bit more about what that score comprises and then what it would be able to tell the user?
Yeah, so the downlink essentially has an information about the location, the fault, right? Which is, again, one of those 6 key failure modes. The fault probability, because we run this through a classifier and we have a confidence score. The health score, which is defined in the pre-processing step, right? It essentially says, okay, based on these agronomic indices, what is the general health, right? Like how can we look at this holistically? And then of course you have the timestamp so the farmer can go look at it.
Time. Thank you.